I want to talk about the final optics. This is where a lot of action happens. This is where you have to do several things. Not only do you have to go from infrared to ultraviolet, and I'm talking about from 20 kilojoules to 10 kilojoules of ultraviolet, but you have to do other things also. We changed the shape of the beam on the target at this point. Depending on the experiment, we want spot size as small as 150 microns, as large as a few millimeters, depending on the type of experiment we have. And we do this with combinations of doublers, triplers, phase plates, and focusing lenses in order to do that. This, again, is a very highly complex and actually, to me, a very beautiful optical system. There's many surfaces. When you're doing systems like this and you have tens of kilojoules of UV flying around, that means any ghost you have now can have literally 100 joules per square centimeter in reflection and will destroy any optic anywhere near it. And so you have to think about this extremely carefully. This has meant that we have had to develop new computational techniques for ghost analysis and the like. You have to think about gravity sags and stuff like that in ways you really wish you didn't have to think about. It's a very interesting system. We also have debris shields because remember the target, it's small, but when it reaches about 100 million degrees, doesn't look like a target anymore. It vaporizes, and it's you get a variety of scales of shrapnel coming off of it, from atomistic, to to nanometer to as large as micron size, but they're moving at high velocities, and they can do a lot of damage to optics. So how we do debris shield technology and the like has also been a very interesting part of the work that has happened here. Most importantly, we've had to develop optics that can take this 10 joules per square centimeter ultraviolet. Lasers like Nova, Omega, any lasers that are generally operating now, previously to NIF, operate at 3/4 of a joule per square centimeter. Just think about how big this laser would have been, actually it wouldn't have been, if you didn't have optics that could handle this kind of beating. And we have developed techniques in not only bulk materials, but finishing techniques, cleanliness techniques, coating techniques that are becoming, hopefully, more and more a part of the industry that we are here for today. And we have other ideas that hopefully will double or triple that, and we'll be publishing that in the months ahead. That will bring us hopefully to the 20 joule, 30 joule per square centimeter damage points for short pulses. We also had to figure out how to do rapid growth crystals. This is a lot of stuff. Each beam. So we did this for KDP, DKDP, or deuterated KDP. We generally do the traditional, but we can grow this crystal, which is, if you want to call them pounds, is 750-pound crystal, 200 kilogram plus crystals in 60 days. These are very high-quality crystals. We've used a lot of material science, computational techniques to understand how to do this and have been publishing a lot about this. And I think it's changing the nature of the crystal activity. Finally, we have an integrated control system. This laser actually operates itself to first order. It's a 3-hour countdown, generally including the target alignment. We started off, having a lot of humans in the loop. Right now we have 2 million lines of code, and every single beam line and all the diagnostics and the target, are on their own. It's a very distributed system, and it's only at T-minus 100 seconds when we start charging the capacitors that the main computer or synchronization computer takes over and queries, the system for readiness, and then brings the countdown into sync, following it down to T-minus 1 second, where it takes away control from the individual beam lines, assumes all control, and then fires the laser. It's kind of an interesting system because, it's like a big countdown, but it's over in a microsecond, so in the flight time of the laser. This is how it looks. This is actually the control room of the NIF. This is how it sounds in real life. Of course, this is not how it looks. But that's a 20 nanosecond pulse. This gives you scale. And you can see the glass as it goes by. And we're going to head to that Pockle cell right there so it comes back through it. It actually plays music. Okay, now we're going to go through the Pockle cell again. And so now it's out of the beam. Go through another set of glass, through those transport spatial filters. We're going to just watch a few of the beams right now. And this is in that switch yard. We'll just look at it. Now we're going to slow it down a little bit more. And we're going to turn the beams green, blue, and focus on the target. Now this is a 20 nanosecond pulse, so you can watch the target go by. This is a little gold capsule. It's about the size of a pencil eraser. It's now a 3 million degree oven. You know, at around 10 nanoseconds, we now have an X-ray bath on this target, which could be plastic. It ablates and blows it in at about 1 million miles an hour. And when it's about 100 microns across, you know, in theory, we get burned. At that point, you know, as I said, the temperature's gone up to 100 million Kelvin or centigrade, as you choose, and the pressure is around 10 million atmospheres, and the density is 1,000. You know, those are the conditions that exist for DT fusion. And it actually starts bootstrapping at that point, and it goes up. You know, the temperature goes up to probably around 700 or 800 million degrees for a few picoseconds. So this time scale is you build a laser for 10 years, you fire it, the time of flight is 1 microsecond, assemble a target in 20 nanoseconds, it burns in 10 picoseconds. So that's the game. This is actually how it looks. Of course, you never get to see this. As I said, 3 different views of the same thing. Now we do it 100 times slower. There's no information, but it sounds cool. Bring up the sound. Okay. It's a nice, you know, if you lived on the East Coast and moved out to California, you missed that sound. Okay. Okay, just to say this, you know, I want to say this laser works, you know. It meets all of its specs. In fact, it exceeds all of its specs, you know, and there's a lot of things about this laser that are interesting. The 3 omega pulse shape, this is a 540 terawatt pulse, and you can see that very low front-end pulse on your upper left. That's really down about a factor of 200. That's when you start shocking the thing. You see the near field profile is quite beautiful. It's around contrast ratio of 10%. The focal spot in this case, which was just a raw focal spot, is 140 microns, and we put just a 90 gigahertz bandwidth on it. But we can do other things too. You know, this is more like an ignition pulse would actually look. You can see that front end, that's used to melt the beryllium if you're using a beryllium target. You want a bigger spot size so you don't have LPI or laser plasma interactions. It has a lot of bandwidth on it. We can do a huge amount of things. It's a very flexible laser, and it's a very precise laser. We can time it up. It's hard to see this. I'm really sorry. I didn't realize what a big room this was. I would have changed the view graphs. We can time it up to around 14 picoseconds, all the pulses. And the only reason we can't time it any better is we didn't spend any more money on street cameras. And also we can aim all the beams, which I find remarkable, to less than 60 microns RMS pointing error. And just to go over that, that's, you know, diameter of your hair is about 100 microns. So all these beams can be controlled to that level. In fact, we think by a year from now we'll be at 30 microns RMS pointing error. This is a terrible view graph, but if you're an aficionado of this, it has power versus energy. It just shows that we have tested this laser in all kinds, every environment that we know that it will ever be used in.